Hi, everybody. My name is Ali Trollier, and I'm coming to you from Eco Oxygen Technology. We call it Eco2 because of the O2 is oxygen. Welcome to this fifth installment of our webcast educational ongoing series. And today we're going to be talking about impaired waterways, restoring impaired waterways. Some of the terms we're going to talk about are water quality impaired streams, streams that are listed as 303D, streams that have TMDLs. I'm going to tell you what all that stuff means. And specifically, we're going to be talking about loads that are biological, organics, BOD, or dissolved oxygen impairment. And the idea is that we're going to try and think past aeration. With aeration, you can get to a certain level of dissolved oxygen. But what if you could go beyond that? We're going to talk about what the advantages of using pure oxygen are and how those are used for restoring impaired waterways. So let's dig in. A little bit of background here. The Clean Water Act has several sections, and one of them is Section 303D. And this is a section about polluted waterways. And this is a federal law that's administered by the EPA. And this federal law requires all states, territories, tribes, etc., to create and maintain a list of all waterways that are not able to meet their current and applicable water quality standards. Then they must also develop a TMDL to meet those water quality standards. So a TMDL is a total maximum daily load. So really what that is a calculation of how much of a certain pollutant a waterway can receive. The TMDL must also include a plan for restoring that waterway and how to allocate load reductions. So if you're a water quality manager or in charge of a waterway, and a lot of these words are making sense, TMDL, you've got a 303D listed waterway, and now you're going to make a TMDL. A lot of this may make sense until you see allocate load reductions, and you're thinking, how do I do that? Where do I do that? We're going to take a little bit of a dive into that. But first, let's just take a quick look at what the map of impaired waterways looks like in the US. Of course, we don't track this for anything else because it's a federal law. So in the United States, since 1972, there have been a total of over 40,000 impaired waterways that have been listed. Currently, that number is smaller because they come off of the list as they get a TMDL and then their restoration plans are implemented. So that number does change, and this was established in 2014, this current map. And so all of those that are shown in red are 303D listed impaired waterways, and it's just an incredible volume. And so when we take a look at how many waterways are impaired and we think of what can we do to improve the water quality in these rivers, we've got a few options, and I'm going to discuss those in a moment. Taking a deeper dive into one state, this is an example from the state of Tennessee, and this map is actually from 2004, but this map shows all of the streams that were currently listed as 303D in the state of Tennessee. So there's a lot of rivers there, and you can see a lot of them are interconnected. So adding oxygen or reducing a load in one part of the system may have an impact on a downstream part of that system. But you can also see that with so many impaired waterways, you can imagine how difficult it would be for the State Department of Conservation to allow new permits or new NPDES permits for additional discharges into these already overloaded waterways. So this could prevent progress or growth for municipalities and industries that would be discharging into these streams. But what this law does, the 303D law, is that it prevents sacrificing water quality for progress or growth. Now, some people may think that that's a bad thing, that we're inhibiting progress by protecting water quality. But things could be much worse, as seen in this photograph in other countries where they don't have things like the Clean Water Act and Section 303D. They are allowed to pollute and discharge and not face fines, and then you end up with really, really poor water quality. So I'm grateful for the Clean Water Act. But say you're on one of these impaired waterways and you've got to figure out a way to clean this up, restore the waterway, either reduce loads or improve the water quality. So let's take a look at where water pollution comes from. This is a diagram that a lot of people have probably seen many times before. I stole this one off of Google, so thank you, Google. But I think it shows a really good distinction between point sources and non-point sources. So you can see point sources are the discharge from a wastewater treatment plant or a wastewater discharge from, say, a factory or an industry. So those would be point sources, and those are things that are regulated and could possibly be controlled. Hopefully they are controlled. Non-point sources include stormwater runoff, agricultural runoff, animal feedlot runoff, but the word runoff indicates that these are non-point sources, and they are very difficult to control without significant infrastructure changes or changes in practices for farming or development and stormwater runoff. So the bottom line is that non-point sources are a little bit of a hard target if we're going to try and reduce load. In stream, you could treat in stream, but that could end up being a very large project. But the one thing that you can go after are those point sources. And we don't want to punish them for doing a good job by making them do a better job, but those are the targets that can be hit. And so those are what we will discuss today. So if you've got a stream that has limited BOD assimilation capacity, that's basically how much BOD that river can handle to receive each day without impairing the water quality. So the organisms and the life inside the stream are able to assimilate that BOD up to a certain point. So once that's limited, that assimilation capacity of a stream is limited, you've got a few options here. Just like we talked about previously, you could try and reduce the non-point source pollutants, stormwater runoff, agriculture. These are things I put in a red X by it because it's difficult, it's time consuming, it's costly, and it's an uphill battle, but I encourage all to proceed down that path nonetheless. But we're going to continue talking about what other options are available and that may be a little bit more cost effective and an easier target and way to improve that waterway without making significant infrastructure changes. The second option B there would be to just stop progress. No new permits, no new discharges. Doesn't seem like a very good option either. Option C is to just continue polluting. Just let new factories come online and let them discharge into the stream. Violations be what may. That's not a very good idea either. I think you'll all agree with me. So we get down to option D, which is reduce point source pollutants or loads coming from those sources that we can identify. And we can limit and we can control and we can probably find funding. So let's take a look at what that looks like. If you need to reduce a BOD load coming from a wastewater treatment plant, you might say, okay, well, we would be looking at advanced treatment, where we would try and further reduce that BOD from its secondary effluent levels of maybe 50, 40, 30 milligrams per liter of BOD, and we would try to get that down as low as possible. So let's just say that with advanced treatment, we may be able to reduce 40 milligrams per liter of BOD. Alternatively, consider adding supplemental oxygen to offset that BOD. So you've either got biological oxygen demand going into the river, or you can offset that oxygen by feeding oxygen. So supplemental dissolved oxygen is a very valid option for reducing point source pollutants by offsetting BOD with supplemental dissolved oxygen. And it may surprise you, but you can get up to 40 milligrams per liter of dissolved oxygen quite easily by using pure oxygen gas and a very good dissolution method, like the Spice Cone by Eco2. So when people would, if a plant was to say, all right, let me take a look at supplementing dissolved oxygen in my secondary treated effluent before it goes into the stream, what would that look like? Well, you've got a couple options again. We're looking at aeration or oxygenation. If you look at aeration, there's a couple of common methods, which is the first one would be a cascade, where the water becomes turbulent and has contact with the air and is able to dissolve some oxygen into the water. And you can get up to about 4 milligrams per liter reliably out of a cascade with the correct hydraulic conditions. Alternatively, with diffusers in a basin, pumping air, you can get that dissolved oxygen level up to about 8 milligrams per liter. Now, if you were to go to the oxygenation side and decide you're going to inject pure oxygen and dissolve that pure oxygen as much as you can, without adding any pressure, you can dissolve up to 40 milligrams per liter of DO. So consider the advantage of getting 5 times more oxygen by going with oxygenation instead of effluent aeration. Let's take a look at some examples. Now, here are 2 plants in Georgia that are discharging into the Savannah River that were required to reduce their BOD effluent load. And just a little bit of statistics on these plants. They're both about 1 MGD average daily flow, and their state permit to allow a higher BOD was to ensure that they have a higher DO to offset that BOD. And so both of these systems were designed and are operating to dissolve 30 milligrams per liter into that effluent. And this is what those systems look like. One has an oxygen generator and one is using mini bulk oxygen gas. They're both using a Spice cone, and they pump a small side stream through that cone off of the effluent, add the dissolved oxygen, and then feed that right back to the outfall. These plants have both been operating for a couple of years, and I can share more information on either of them to anyone that would like it. So if you come to a point where you need to consider how to reduce point source loads, try thinking beyond aeration, at least for biological TMDLs. And consider most wastewater treatment plants have a discharge permit that includes a DO requirement. However, that's rarely over 6 to 8 milligrams per liter. And that's because of the technology of aeration and the concentration of oxygen in air. So that DO level is limited by the nitrogen content in air. However, with pure oxygen, a DO level of up to 40 milligrams per liter is actually quite simple, as long as you have the right equipment. So just for a moment, step back and think what the added capacity for an impaired waterway would be if one or more or all wastewater treatment plant effluents were continually delivering surplus dissolved oxygen to that impaired waterway. What would that be like? If you could increase that BOD assimilation capacity of a stream, what would that do for your local economy and for the local water quality? Several people are doing this currently. This isn't a new idea. You can increase the BOD assimilation capacity of a limited stream, and those methods have been called BOD offset, net zero ultimate oxygen demand. These are terms in different states. Many folks would recognize the term effluent aeration, post aeration, or effluent oxygenation. Other methods of increasing the assimilation capacity of a stream would be in-stream treatment, either oxygenation or aeration. Also, lake surface aeration has been used several times, as well as river surface aeration. And we also have many examples of lake oxygenation. Also hypolimnetic oxygenation, which is for deep reservoirs, often used for reducing nutrients or iron and manganese or algae on those reservoirs. Again, I'd love to provide more information on those topics if it strikes anyone. Please contact me. Just keep in mind that with aeration, you can add about 4 to 8 milligrams per liter of DO, which is equivalent to a half to 1 pound of oxygen per MGD. And if you think for each pound of BOD, you need about a pound of oxygen, that is a little bit debatable on that 1-to-1 ratio, but it's pretty close to that. And so if you just convert those pounds of DO to pounds of BOD, by aerating, you can increase up to about a pound of assimilation capacity per MGD. Now with oxygenation, you can multiply that times 5 because there's so much more oxygen in pure O2 than there is in air. So with oxygenation, you can easily get up to 40 milligrams per liter, which would be an equivalent of about 5 pounds of BOD assimilation capacity per MGD treated. So again, think, if all wastewater plants did this, how much more BOD assimilation capacity would be in all rivers that are BOD impaired or limited? So you may be asking yourself, well, how do we achieve such a high dissolved oxygen? Is this Spiess cone magic? Well, unfortunately, it's really great, but it is not magic. It uses science. And what we've done, what Dr. Spiess has done with the Spiess cone is actually optimized the variables in Henry's law, which is shown here. Really what it boils down to is inside the Spiess cone, we're maximizing the contact area between the gas and the liquid, and we're maximizing the contact time of the gas and the liquid. And at the same time, we're increasing the gas concentration. So instead of air with 21% oxygen, we're using pure oxygen gas or high purity oxygen, which is really close to 100% concentration. So that's how you can increase that saturation level and how we can do it so efficiently. I'm going to give you a couple of examples of streams that are increasing their BOD assimilation capacity with either aeration or oxygenation. And one example that I'd like to highlight was pointed out to me by Dr. Spiess, and this was completed a couple years ago, but the Chicago canals or the Chicago River were listed on the 3OD list in Illinois for several years, and they were able to develop a TMDL. And I've got just a copy of the front page shown here. It's a pretty hefty document, and you can find that. All this is public, and it's hosted by the EPA in the state of Illinois for this particular one. And then next to it is a map. And if you look closely, you can see in-stream aeration station up here, another in-stream aeration down here at Webster Avenue. And so what they did is they actually took that stream and put beautiful elevated aeration ponds in it. So throughout the city, they made beautiful ponds. I do not have a figure on what the cost of this was, but I can imagine that it's a pretty big number. But look at what they've done. They've restored an impaired waterway, and they've made a lot of really beautiful scenery there in the city. Another example I'll show you is with using the Eco2 equipment, the Spiess cones on the Savannah River, where they're doing river oxygenation. And so this was another river that was impaired for dissolved oxygen. It had low DO in this river, and several different factors came into this, but EPA and the Army Corps of Engineers were involved, and they came up with a plan to restore this waterway. And part of that plan was to oxygenate the river. And so here you can see a very large system. It's adding 40,000 pounds per day of dissolved oxygen into the Savannah River Harbor. This system has been operating for about a year total, and it's getting really good results. A lot of that is available online through the Army Corps and also on our website. So I'd like you to think about how you can go beyond aeration. Everybody's doing it. Jump in, the water is warm. Call us if we can help. We love talking about dissolved oxygen and how we can help you think beyond aeration. Again, my name is Allie Trollier. I'm with Eco2, and thank you so much for tuning in. Goodbye, everybody.